perfect. Thank you so much, Walter, for the nice introduction that you give for me. So let me share my screen. Okay. Uh, can you all see my slides?
Yep, we can see your slice.
Okay, perfect. So are we good? Can we start?
Yeah, we can start. Go ahead.
Okay, perfect. So thank you everyone for having me. It's a pleasure to give a presentation to, to FIU, to to ARC and all the people there. I'm very familiar with. Coming back and still keep having the relationship with some of you and being able to collaborate in different projects. So that's been really good. Um, for me, that I've been able to continue with that connection with some of you. So today, my presentation, I'm going to talk about the ALTEMIS project. ALTEMIS stands for Advanced Long-Term Environmental Monitoring Systems. This project was initiated by SRNL in collaboration with Berkeley Lab in 2020. And the focus of this project is to develop a long-term monitoring strategy for contaminated sites by using state-of-the-art tools and technology uh, to be able to improve the monitoring of those contaminated sites. So some of you may be wondering, why do we need to improve the long-term monitoring of contaminated sites, and why we cannot just keep continuing with the traditional approach? For some of you that may not know, the traditional approach for monitoring sites is to go out to the field, collect water samples, and send those samples to labs for analysis, and that way you are monitoring your contaminants. So what is wrong of of doing that type of approach for monitoring? To answer that, there is nothing wrong with that approach, but what you may have to kind of like think about what is going to be the objective of monitoring. So, and I'll give an example. For those contaminated sites where the contaminants are either destroyed in situ, or the groundwater is extracted to remove those contaminants, the objective of the monitoring is to ensure that the remediation is effective and the contaminants are decreasing with time until these contaminants do no longer possess a threat to the human health, as we can see here in that figure on top, for a pump and treat system where you extract the groundwater, remove the contaminants until you don't have those contaminants in the subsurface. But what happens to those contaminated sites where attenuation-based remedies have been implemented? And we can see an example at the bottom right. The contaminants for this type of sites, the contaminants will remain in the subsurface and especially for those contaminants like radionuclides and heavy metals. They're not going to be destroyed. They're going to remain in the subsurface for hundreds, even or thousands of years. So the traditional way of monitoring these type of sites will be very costly, because you can imagine that you would need to collect water samples for hundreds of years, and the cost is going to be unthinkable. So one approach that the ALTEMIS project has been developing is to, instead of focusing on the contaminant concentration, what we will need to emphasize more is to monitoring those factors or variables that um, cause the remobilization of those contaminants. By doing that, will be more efficient because you will be able to detect those leading indicators that in the future is going to remobilize those contaminants. So you will be, kind of like more effective, be able to detect those conditions like at the early stage. So it's going to give you some time to do something to fix the problem. And here is kind of like an example to compare, both ways of monitoring, the traditional versus this new paradigm in monitoring that we want to establish. So this is an example of from this old idiom saying that there is no point in shutting the barn door after the horse is gone. So you can think of it as the horse being the contaminant inside the barn. So with the traditional way of monitoring, you would put a monitoring device in the horse, and you don't know, what conditions, can cause, like maybe someone forgets to close the door or the lock gets damaged, and then the horse escapes from the barn, and then suddenly, yeah, you have the horse outside, and it's kind of like the contaminant. You cannot do anything. It's already in your, free mobile. So the approach that we're trying to establish is that instead of monitoring the horse, the contaminant, what we can do is to monitor for those variables that um, you know can indicate you when there's going to be the condition for the horse to escape. So in this case, for the barn, you would put sensors in the doors or maybe in the lock that could warn you, if someone forgets to close the door or the lock, is getting into unstable conditions. It's still the horse is inside the barn. It hasn't been escaped yet. So this gives you some time for you to do something about it before the horse escapes, or in the case of contaminant sites, before the contaminants get remobilized and contaminate and move in the groundwater. So this is kind of like the approach that we're trying to establish with the ALTEMIS project. So to test this approach, we selected the F area at the Savannah River site. The reason that we selected this site specifically is because it's a well-characterized site. It has more than 30 years of monitoring data, and is in the later stages of the remediation. So we kind of like selected this site to test our approach. So I'm just going to give a brief introduction of the remediation history for the F area. So the F area, if you can see my mouse, the F area is located in the northern central part of the Savannah River site. And the F area consists of 3 online seepage basins that receive low-level radioactive waste from the processing of uranium slugs and fuel targets that created all of these waste that ended up being discharged into these basins. So at that time, it was thought that the contaminants in the waste would seep into the subsurface, bind to the sediment, and stay there. This was true for many radionuclides, but there were some contaminants like uranium, strontium, iodine, technetium, tritium, nitrate, that due to the acidity of the waste, that kind of like help mobilize those contaminants. So you can see here in this figure, small figure, those contaminants um, got mobilized through the vapor zone and then reach the groundwater. And once they reach the groundwater, they created this plume that is that then it moves with the groundwater flow and then reaches to these wetland areas and formal branch as a discharging point. So the in the early 70s and 80s, um, the site did some of the studies in the wetlands and also formal branch, and we were seeing that the trees were dying in those areas, and it was due to the waste that the groundwater plume that it was already reaching those areas. So the site in 1988 decided to close the basins by first dewatering the basin, chemically stabilizing the basins, the bottom of the basin soil, and then the site put a protective clay layer on top to close those caps and not allow rainwater to infiltrate through that. So that was kind of like the first remediation step that the site took. The second one was to treat the groundwater. So in 1997, the site installed a Pullman treat system. So you can see here in the figure that the groundwater was captured downgrading from the basins with these red dots that you can see here from extraction wells. And then that water was taken to a treatment facility to remove all the contaminants except tritium. And the treated water was reinjected upstream of the basin. So the idea was to um, remove the contaminants and then keep tritium kind of like in a closed loop. And by doing that, we would allow the tritium to naturally decay with time. But by 2003, the site realized that we that it was getting diminishing results. Still, there was a lot of groundwater plume reaching the wetlands. It was very costly to maintain and operate this system. It was costing about $1 million per month. And also, he created a secondary waste from the removal of all of these contaminants from the water. So in 2004, the site first did a characterization to see where the groundwater plume was moving, and they identified some low depressions in the tank clay where most of the concentrated part of the plume was moving. And then in 2004, the site decided to install a funnel and gate system that you can see here in this figure, which consists of a wall install all the way to the tank clay from the top surface all the way to the tank clay. And this wall has some gaps in between. And in these gaps, we are injecting, well, first of all, we didn't want to block completely the groundwater. We wanted to allow some, gaps for the groundwater to continue to flow. And the second objective was to, having these gaps to be able to inject an amendment to remove some of these contaminants. So currently we are injecting a base injection to increase the pH of the water. By doing that, we are precipitating and also enhancing the absorption of uranium and strontium. And since 2004, that technology has worked very well, and we see that strontium and uranium concentrations are decreasing with time. So this that strategy is working. And in 2015, we started to treat silver because the base injection does not address all the contaminants. So to treat iodine, we started in 2015 to inject a silver chloride particle in the central gate. And by doing that, we have seen how iodine is getting a decrease with time. So those are the two methods that we have been applied that are currently working to address those type of contaminants. So to the now that we have that history of the site, to develop this long-term monitoring strategy for the F area, what we did was we went back to the and revised the conceptual site model, and then identify those locations where there is residual contamination in the subsurface, and therefore those locations will need to have monitoring to ensure that those contaminants remain immobile. If conditions change, they will not get remobilized. So if the conditions change, we'll be able to detect that. So for the F area, we have these three locations where there is the residual contamination that we call them zones of vulnerabilities, because if conditions change at the site, then those contaminants have the potential to be remobilized. So we have the soil beneath the basin where still there is a residual contaminants absorbed to the sediment. We have the treatment zones at the gates. So in this case, we kind of like have created a secondary source because we are precipitating uranium and strontium and also iodine. So those contaminants remain sequestering at the gates, and there will be the potential, if conditions change, for those contaminants to remobilize again. And the third location that we have and that I didn't talk about is the wetland areas. This is the discharging point of the groundwater. Many of these contaminants have been attenuated naturally in these areas where there is very rich organic soil in that location. So once we identify the location, the locations that we need to monitor, then the next step, well, here is just to show you what would be the goal of the ALTEMIS project. So with the ALTEMIS, what we want to do is to develop and implement this integrated strategy, so we can able to monitor these complex contaminated sites and use these state-of-the-art technologies and remote sensing tools to be more proactive and be able to detect any anomalies or changes in the environment that could lead to the potential remobilization of those contaminants. We want to improve the robustness of future monitoring and also improve the regulatory and stakeholder communication to expedite the closure of complex sites. And with this approach that we are testing at the F area, we're hoping that we can transfer this strategy to other DOE sites, that it can be implemented as well. So for the strategy, okay, so we um, listed those three locations where there's going to be need to be monitored. And in each one of those, what we did was identify what is the vulnerability, meaning what are the factors that could cause the remobilization of those contaminants, what would be the objective of the monitoring, and what kind of tools and technologies could be used to monitor those locations. So I'm going to start with the basins. With the basins, the vulnerability will be like, for example, if the cap that is protecting the basin soil gets damaged or degraded, then it's going to allow rainwater to infiltrate and then reach the basin soil where those contaminants remain attenuated, and it will be the potential for those contaminants to remobilize with that infiltrated water that is going through the Vado zone. So in this case, the objective of the monitoring will be to monitor the cap integrity to ensure no water is passing through, or there is not any increase in moisture, that could also indicate that the cap is being degraded. So there are different type of technologies and tools that you can use to monitor the cap. You can do UAV imaging using LiDAR photogrammetry. You can do geophysics like electrical resistant tomography, or also sensors closer to the basin that can um, monitor for those contaminants and see if there is any leaching and remobilization of some of those contaminants. So for the F area, we selected the electrical resistive tomography system. And here's in this graph is kind of like a conceptual model of what this technology is. This technology is has electrodes that we install on the surface of the cap, and what it does, it measures the soil conductivity. So let's say, for example, that the cap is damaged or degraded, then as you can see here in this picture, water will be able to pass through this protective clay layer and then go into this region here. So that will increase the soil moisture and the water content. So with these electrodes inject a current to the soil, so you will be able to image, in what place your soil conductivity is increased, and you can attribute that to degradation or damage to the protective cap layer. So in last year, we installed the ERT system in one of our area basins in collaboration with PNNL, and the installation is fairly easy. This is a picture of the top of the cab. So what we did is we did some trenches, very shallow trenches, like 6 inches deep. And then we laid down the ERT cable, and you can see in this picture at the bottom on the left, um, the ERT system consists of a cable with electrodes spaced at 5 meters, and and once you lay out this cable, then you cover the cable, and this is the final installation, how it looks like. These cables are connected to an ERT equipment, so what it does, it takes um, um, measurements and measure the conductivity of the soil, and you can um, do it at different frequencies and all of that, and it's going to be able to detect if there is any changes in the conductivity of your soil. So we're using this technique as of right now to monitor the integrity of the caps. Um, it is just to show you some preliminary results that we got from the ERT system, and I'm going to click the video so you can see. So this is on top we have the electrode configuration that is monitoring the cap, and here's the changes in conductivity. As you go more into the red zone, increased conductivity, and in the bottom figure, it correlates with the rain events that we have during the period of September 28th to December, just to show you how conductivity changes in the soil. Okay, so here I'm just playing the video, and then you can see that when we had a rain event, then let me just click a pause. So you can see in our first rain event, since we installed the system, we had some red areas because the top layer of the soil, it gets some water accumulation, but nothing going um, through the cat clay layer, which is in this area right here. So I'll keep it advancing the video so you can see when we had some more rain events during November and December timeframe, how the conductivity of the soil changes, and it's really cool. And in this case, you can see that most of the water, or all of the water, it stays on top of the clay cap, so nothing actually uh, goes below the protective cap layer. So this indicates that, at least for the area that we're monitoring, the cap is still healthy. It's not allowing any water to pass through the clay cap. So most of that water is just stayed on the top of the soil, that will eventually um, run off to drainage ditches that we have at the side of the basins, or it will get evaporated. So this is really cool images that we have from the ERT system that we're using to monitor the basin. Our second location that we are monitoring is the treatment zones at the gates. And as I mentioned before, we are injecting base solution to increase the absorption and precipitation of uranium and strontium at the gates. And we injected silver chloride to remove iodine as well. So in this area, what we want to the vulnerability in this case would be any changes in the groundwater chemistry that could cause the remobilization of those contaminants. So in the case for uranium and strontium, if we allow the groundwater pH to come back to drop to more acidic conditions, then uranium and strontium will become mobile again. And in the case of iodine 129, if we allow if the groundwater chemistry um, um, goes to from oxidizing conditions to reducing conditions, then silver will get reduced and then release iodine into the groundwater. So we have those two factors that could potentially remobilize those contaminants. So to monitor this area, what you can do is to put, sensors that can actually monitor those variables that could indicate when these conditions are going to happen or not. So in this case, we decided to install sensors in several wells for the F area that can actually tell us, the groundwater chemistry, and see if it's going to change in a way that could potentially remobilize some of those contaminants. So, but before I can talk about that, we so we decided to install the sensors, but first we needed to know how many sensors we needed to put in our contaminated site, and also what will be um, the most optimal location to put those sensors. And in this case, FIU, in collaboration with Berkeley, help us to make this type of decisions. So they use artificial intelligence and machine learning systems to first, you can see here, where they took the historical monitoring data and created these reference maps that we can see here. And then with their machine learning approaches, then tested to see how many wells um, we would have to need to be able to replicate the same mapping, and also kind of like reducing the what would be the kind of like determining what would be the minimum number of wells that we would need it to be able to represent this mapping. On that result, it came out, and it for our side, we just need to have like 20 wells that it will be needed. And currently we have like 90 something wells that we currently monitor. But in their results, they show that with 20 wells, it will be more than enough to um, capture the spatial distribution for the groundwater plume. So that's one of the results that they got from this study. Another approach that they took is to see, okay, where we want to put these sensors and what is the best optimization for the sensor location. And they also took a similar approach, and they came up with using again a reference field and then using a machine learning approach to kind of like select the best locations where it could be as close as to the reference mapping. So based on these results, then we were able to do the selection to put those sensors in the wells, and these sensors we installed them last year. In total, this is the map of the site, and then the circles represent the wells that where we deploy the sensors. We install two type of sensors: the Aquatrol 500 for the wells that are closer to the basin, going through the central gate and to the wetlands, because um, and we wanted to monitor more the chemistry of the groundwater, and the Aquatrol 500 measures pH, conductivity, redox, and several other parameters. And the other type of sensor that we deploy was the Aquatrol 200 for wells that are kind of like in the boundaries of the groundwater plume, and it measures conductivity, pressure that can be converted into water level and temperature. And the idea for this is to kind of like see, monitor how the groundwater plume moves, and if the flow changes with time. So the installation of the sensors was fairly simple. And this is a picture of us installing the sensor. So we basically lower the sensor to the depth that we wanted to monitor within the screen zone. Then we put back submersible pump that we have for several of these wells, and then we attach at the side and the telemetry system. So here on the bottom right image is the final installation, where we have the well, then we have the cable protected with a PVC conduit, and this is where we have our telemetry system. So once these sensors are installed in the wells, we practically don't have to go to the well, except to do any maintenance or calibration. So once these sensors are deployed, then they will start sending data automatically. So we don't have to go to the field to take measurements, and that saves time, money, and a lot of effort. So in these slides, it's kind of like just to show you, once we have the sensors and they're transmitting data, then you can go to the website. So the data is transmitted to the cloud, and you can access to the cloud through any computer. You have to have your account, and then it can give you on the right the list of all the sensors that you have, the locations if you want to add them as well. We decided not to, but in any case, and then you can select it, and it's kind of like a really easy visualization of the data that you have for your sensor. And you can change the frequency of your sampling. You can change the uploading frequency as well. And this is kind of like just to show you the display of how we see now the data that we have from the sensors um, so far. What we want to do with all this data and that we're collecting from the sensors, so we want to be able to use it as a surrogate for the traditional way of contaminant sampling or water sampling. So with these sensors, they can inform you better about the chemistry, and you can use it as an analog to monitor for different type of contaminants as well. So right now, FIU is helping us to then again using AI and machine learning approaches. And actually, Himanshu's group developed this um, Python package called Pylem that that you can use the monitoring data from the sensors, so from the water sampling, and you can use these different approaches to give you correlations, different analyze that you can see whether or not conductivity correlates with tritium, with uranium, like in this case right here, or with other type of contaminants. So it allows you to do some type of data analytics to be able to find where you can see similar behaviors with your variables and your contaminants. Also, it allows you to do some cluster analysis as well to see if there is any spatial correlation or variability as well with all the data that we're collecting so far. So Himanshu's group is working on this currently, and I'm getting better with this. But this is also really helpful when we come to the long-term monitoring of sites. How can you automate the process and make the digestion on of the data that you're receiving from the sensors? How you can able to display it easily, be able to analyze it and evaluate it in a more fast and easier way using these new tools and technologies that are coming up. And for the last location that we are um, monitoring is the wetlands. The wetlands is the most complicated location that we have at the F area because and the least understood, because you have a lot of organic matter, you have microbial activity that can influence in the contaminant mobility or attenuation. You have rain events, changes in the water table, that can also changes the conditions of the wetlands. You also have seasonality, like changes in temperatures throughout the year. All of that is complicated and affects the way the contaminants behave and also can remobilize in that area. So for this location, we have tested different tools and technologies that we can use um, to monitor that this location, and I'm just going to talk briefly about them. So with Berkeley, what we did, what we have been doing for the past 2 years is first doing a subsurface characterization to locate some of those discharging areas in the wetlands, um, see what is the thickness of the organic layer and where the contaminants tend to accumulate. So these past 2 or 3 years, Berkeley has come with these three instruments that you can see in the picture on the left, the spectrogamma sensor that can detect where hotspots of radionuclides are, and the electrical magnetic induction meter that can measure the conductivity of the soil and also identify some of those discharging areas, and the ground penetrating radar that you can see here that can give us some information about the structure of the subsurface. So with these three instruments, we have been doing several wall-cover surveys to do this type of characterization. So here I'm just showing some of the recent results we got from that survey. Um, with the electromagnetic induction meter, um, these are the path that we walk in the wetlands collecting all these measurements. And then with this data, we can create this 3D mapping to kind of like show us, in some locations where is actually the groundwater coming to the surface. This is very important because this is the points where the groundwater plume is reaching out the surface and, interacting with organic soil. So it's a very potent tool, so we can know a little better, where these contaminants tend to accumulate in the wetlands. We can also use in combination the EMI and the GPR to see the subsurface structure, see and determine the thickness of the organic layer, in a transect lines, and understand a little bit better and where the tank clay is located, and different materials in the subsurface that will play an important effect in where your contaminants get accumulated in the wetland soil. And in this slide is show you some of the results that we got from the spectrogamma mapping that we did to identify some of the hotspots in the wetlands. So this is the handheld device that Berkeley bought. Berkeley um, uh, um, um, took to us, and they came. So with this handheld device, what we did was to do some walkover surveys, and you can see here in the map some highlighted areas in this location specifically, and in this location as well, that is associated with uranium. So we did a walkover, and and we identified some of the areas where we actually can see some of the contaminants accumulated specifically for uranium. With the same data, then we can um, do a 3D mapping as well that can show us a little bit better in details, the extent and where the contaminants are located. Um, Berkeley, they also have a drone to do flyovers, but in our case, we cannot use the drone because these wetland areas have a lot of vegetation and trees and bushes, so it's difficult to do a flyover over there. So that's why we decided to use the walkovers instead to do this type of radiation mapping. And the next tool that we installed to kind of like understand a little bit better the hydrology of the wetlands and see where the contaminants are accumulating and coming to the surface was the installation of distributed temperature sensors. So you can see here in this picture, this is the temperature sensor. So it has a temperature sensor every 5 or 10 centimeters, so we can get a really nice vertical profile of the soil temperature. And in here on the top part, this jar is where it has the data logger, and the installation is fairly easy. We just need to drill a hole and then push the probe into the ground. Pretty much that's it. The only inconvenience of this tool is that we have to go to the field every 3 or 4 months to download the data because it does not have a way to transmit data remotely. Since these sensors have a very low battery consumption, yeah, we have to go, but we have to go only once every 3 or 4 months, and we use a phone to download the data from each of the sensors, and that's pretty much and it's a simple thing to do. The other task that we already completed to understand a little bit better the wetlands is also to put this type of in situ sensors in several of these locations, again to monitor better the changes in the groundwater chemistry and see how does that affect the mobility of the different contaminants in the wetlands. So we install shallow wells at several locations, and we did it by hand. And this is kind of like in this picture is the final installation. So per each location, we have two shallow wells. One that is monitoring the surface water, and the other one is monitoring the groundwater. So we want to understand better the groundwater surface water interactions, and we're measuring both several parameters: temperature, conductivity, DO, pH, water level, turbidity. And here I just wanted to show you how, here in the wetlands is, more complex and dynamic environment. You can see here from the ORP that the surface water actually goes a couple of days goes to more oxidizing, and then it drops to more reducing. So you have like this fluctuation that we have seen, that if we were doing like only um, traditional sampling, we will not be able to kind of like capture these type of dynamics that happen in the wetlands. That, is very important to understand the um, behavior of these contaminants in the wetlands. And the last technology that we're planning to install in the F area that we haven't done yet, but soon we'll be able to, is to put this air monitoring system in one location in the wetlands, and this is for iodine. We don't know if iodine, if there is any emissions into the air for iodine in the wetlands. So this is kind of like part of a study that we want to do to monitor the air and see if there is any iodine in the wetlands that is being emitted to the air. So we'll soon be able to install this technology. So we have all of these sensors being deployed in the field, and now we are collecting all of these data. So what are we going to do with that? So to handle that, we have an external collaborator, and he's designing now cloud-based data management system where we can upload and transfer all the data that we're getting from all of these sensors that we have deployed in this system, that is going to be accessible for the ALTEMIS team. And, we can go there and we can do quick visualization of the different data that we have for the sensor network. We can download it and use it, for our own research purposes. So this is something that we are currently working on. That still is not completed yet, but we'll soon start having some of these capabilities as well, to put all of the sensor data. And lastly, this is kind of like the picture of including all of the sensors that we have deployed so far: the ERT at the basins, the in situ sensors in the wells, the temperature probes in the wetlands, and also some of the in situ sensors in the wetlands as well. So right now, the next steps is to continue collecting the data, evaluating how these sensors behave, how robust they are, developing this data management system to house all of this information that we're getting, um, using statistical tools to optimize the monitoring, and also AI and machine learning approaches to help us out a little bit to digest all of the data that we're receiving and make some predictions and give us some detection when we see some anomalies or some behavior that we are not expecting to see for the data. Kind of like help us out to identify, in what locations that is happening. So with that, I am concluding my presentation. I want to give thanks to all the collaborators that have been helping us to you develop and implement this long-term monitoring strategy. So we have from SRNL our team, and we have also collaborators from Berkeley Lab, from MIT, from PNNL, some private consultants, and of course um, really good people in TELIEM from Florida International University. So with that, I thank you all for listening to my presentation. And if you have any questions, I will be more than glad to answer them.